Dear mathematicians, we are going to be talking about Dirichlet conditions. These are conditions for which a Fourier series must exist. Without these conditions, we cannot have a Fourier series. And they also define the convergence conditions of a Fourier series. So this discussion will talk about what those Dirichlet conditions are, like periodicity, bounded variation, and so on and so forth. Then we'll be looking at a few examples to understand more of these Dirichlet conditions. Remember to subscribe, comment, and like. Dear friends, for a function f of t to be represented by a Fourier series, it must satisfy certain conditions known as Dirichlet conditions. These conditions ensure that the Fourier series will converge to the function f of t at most points, and these are the conditions. So we are saying usually this f of t, this function, for example, f of t could be equivalent to a given function, say t. But now if we take it to a Fourier series, it becomes approximate. So f of t will be approximately equal to a Fourier series of cosine and sines. But now these conditions ensure that this series always converges to the function f of t at most points. Condition number one is that the function must be periodic. So if it has a period t, it means there exists a smallest value t whereby f of t is equal to f of t plus t, equal to f of t plus nt, whereby n is an integer. Take an example, a periodic function like sine x. So this function is periodic with the period, let us take period t equivalent to pi. So if we say that sine of x, this is the same as saying sine of x plus 2 pi. This is the same as saying sine of x plus 4 pi. This is the same as saying sine of x plus 2 pi n. So what does this mean? If you had a function, for example, this sine x, and you're saying, I want sine 30. This is 0.5. But if you also get your calculator and get sine 30 plus 2 pi, this is also 0.5. Sine 90 is equal to 1. But also, if you say sine 90 plus 4 pi, this is also 1. So for that matter, if you have such a function that is periodic, then it means you can express it as a Fourier series. It cannot be expressed or represented by a Fourier series if it is not periodic. Number two is that there should be finite number of discontinuities. So the function f of t must have a finite number of discontinuities within one period. Infinite discontinuities are not allowed. So take an example. If you have, for example, a square wave, you can have a function defined by this. Maybe this is negative 1, you have 0, you have 1. Maybe this is, let me say 1, this is also 1. So there is a discontinuity here. This is how it looks like. And this is one period, equivalent to 2. So this is allowed, and this function can be expressed as a Fourier series. But now, if at all you have infinite number of discontinuities, like this, now such kind of a function, you can see you have very many discontinuities in just one period is equal to 2. This cannot be expressed, cannot be represented by a Fourier series. This one can be represented by a Fourier series. So it must have finite number of discontinuities within one period. You should also have finite number of maxima and minima. Take an example with maybe a sine wave. So assuming a sine wave, you have 0 at 2 pi. You have a pi here and 2 pi here. So that means the period is 2 pi. Now, assuming you again have a similar function like this, you have 2 pi and 0. Then you have a function like this. This is t. Here you have infinite number of maxima and minima. You cannot even count the number of minimum points and the number of maximum points. If that is not possible, then you cannot have a Fourier series. This one can have a Fourier series. That's what we're talking about. Then it should also be absolutely integrable, meaning that you can get the integral of that function over that one period. And over that one period, meaning if the integral exists, then if you integrate that, the value is always going to be less than positive infinity. And this ensures that the Fourier coefficients can be calculated. So let's also talk about bounded variation. The function must have bounded variation over one period. This means that the function does not oscillate infinitely within a given interval. So meaning the number of changes by which this function is going to be changing or varying, you could have something like this. So if this is one interval, maybe this is a negative pi, this is pi. This is f of t, maybe this is t. This function cannot have a Fourier series because you can see between, within just one interval, you cannot count the number of minimum and maximum, and you cannot even count how this function has varied. Because you can see here, when it reaches here, it varies. It reaches here, varies a different way. Reaches here, varies a different. This one cannot have a Fourier series. But if it has a bounded variation, meaning that within a given within a given interval, the function is varying finitely. In other words, you can tell the number of times it has varied. So we need to look at the key difference between bounded variation and finite minima and maxima. Take an example, a function that has a finite number of maxima and minima. This is so because it will not oscillate infinitely many times within a finite interval. For example, a square wave has a finite number of maxima and minima, 2 per period. One maxima and one minima at -1. You can see this is a square wave. So you find you have at -1, you have a minima and you have 1, and that is a maxima. And the range is, for example, let's take an example from, let me say, -3, 0, maybe it's 3. So over that period, we have finite number of maxima and minima. Now look at this other function of f of t is equal to sine 1 out of t. Near t is equal to 0, you have very many maximas and minimas. You can't even count them, very many of them. So this one cannot have a Fourier series. But this can have. If, for example, this has a Fourier series, then it is going to be like this. It's going to have something like this. Then this also is like this, something like that. Then this is a plot of a Fourier series. So let's look at the bounded variation. Okay, we have seen what finite maxima and minima is. Let's look at what bounded variation in details also is. So bounded variation, you'll have the total amount the function changes or oscillates over a finite interval is also finite. Maybe you can say it has changed 2 times, maybe 3 or 4, but it has to be finite over that interval. This is stricter condition than having finite number of maxima and minima. The function can have a finite number of maxima and minima, but still not have bounded variation if the changes in the function are too large. So let's look at finite maxima and minima, but with unbounded variation. Look at this function. Its plot is like this. See, near you'll see that it will have finite number of maxima and minima in any interval, not including t is equal to 0. Like you see, from negative 0.15 to this point, you see you have this minima and that maxima. Here you can see. But as you go to t is equal to 0, the thing has very many minimas and maximas, even when you go to the other side. So at t is equal, near t is equal to 0, the function oscillates infinitely many times and the total variation becomes infinite. Thus, it does not have a bounded variation. So such a function, again, we cannot represent it with a Fourier series. So what if it has a finite maxima and minima and it is bounded? This is how it is going to look like. You have a square wave. This square wave, as we have already seen, it has a maxima and minima, and then the variation over one period is actually going to be, so if we talk about total variation over one period for this function, this is equal to 1 minus negative 1. And you have only two variations over one period. So meaning this is having a bounded variation. So in summary, we are saying this is having a bounded, has finite minima and maxima, plus it has bounded variation. So we are saying it is periodic with one period t. It has one discontinuity per period. You can see it here. So just one discontinuity here per period. Then it has a finite number of maxima and minima. Those are two. It is absolutely integrable. You can integrate this, for example. You can integrate from 0 to t out of 2 of this 1 with respect to t. You can also integrate from 0 to t from t out of 2 to t, okay? Integrating negative 1 with respect to t. So that means it has an absolute integral. Then it is also having a bounded variation. So thus a square wave satisfies the Dirichlet conditions and can be represented by a Fourier series, as we had earlier on said.